things. All right, so today is Unsafe Rust, and so we're going to be talking about why you would want to use Unsafe Rust, why you wouldn't want to use Unsafe Rust, and then how you can actually write Unsafe Rust yourself. And we'll only be going into a few examples, but there are plenty of different ways, and this is sort of just a way to dip your toes in a 40-minute or a 50-minute lecture. So let's talk about the first thing. Why should we use Unsafe Rust? I'm also going to double check I'm recording, which I am. Okay, so why use Unsafe Rust? Well, this is the answer from the Rust book. It's when the compiler tries to determine whether or not the code upholds the guarantees, it's better for it to reject some valid programs rather than accept some invalid programs. And so while it may be okay, the Rust compiler isn't able to tell you that. And so as a result, you can use unsafe code to tell the compiler, I know what I'm doing, don't worry about it, but you do it at your own risk. If you're wrong and you don't know what you're doing, you might actually cause more problems than you're solving. So basically, in short, as I said, sometimes we just know better than the compiler. We know what's going on and the compiler doesn't. And so in these rare occurrences, we need to be able to tell the compiler we know something that it doesn't and something it cannot check. And so this is what Unsafe Rust is for. And so I want to point out something here, that there are two words that are very, very important, and those are rare occurrences. All right? The chances of you running into an issue where you need to use Unsafe Rust are relatively rare. And in those situations, there are ways to not use Unsafe Rust. So it really depends on your use cases, but make sure that you're aware when you're using Unsafe Rust, because it can cause many, many more problems than you otherwise would have. And it's so rare and so unsafe, as it likes to call itself, that Ferris, the Rust mascot, has a special look for whenever there's unsafe code around. So yeah, say hi to Ferris in the Unsafe Rust forum. So let's talk about why we would want to use Unsafe Rust. So there are a few different reasons. We're going to go into some of them, and then there are plenty others that you might use it, but they're less common. So the first one, calling code written in other languages. This is the one that I put at the top of the list because I think it's the most applicable. If you have code that you wrote in another language, you might want to use that code because you don't want to have to rewrite it in Rust. It's a simple system, right? If you write how to come up with some sort, or if you develop some sort of machine learning algorithm that's written in C++, then you never need to worry about writing it again because you can just call it directly from Rust. And somebody asked what species Unsafe Ferris is. Ferris is a crustacean, so I'm assuming a crab. And so Unsafe Ferris is also a crab. But yeah, so Unsafe Rust, it's calling code in other languages, right? And so it's very important that you are aware of when you're doing this, and we'll talk about why, but it's really, really useful because it saves you so much time. So another reason is writing high performance applications. So there are some times where the Rust compiler and the Rust borrow checker and a bunch of other different tools that Rust has to make Rust safe are going to cause a decrease in performance. And in those situations, you will want to be using you'll want to be using Unsafe Rust because you'll be able to just squeeze that extra ounce of performance. And the final reason is connecting with memory mapped one of the other reasons is connecting with memory mapped hardware. So this is like if you wanted to control a motor or use a display or something like that, right? You can use that by connecting directly to the memory that the hardware is reading from. So why use Unsafe Rust when it comes to calling functions written in other languages? Well, as I said, many libraries and functions that we want to use aren't written in Rust. Rust is a very new language. It takes time to write those kinds of languages or those kinds of libraries. So instead, what we want to be doing is writing them or writing our wrapper that connects those languages in Rust, but then using C++ or whatever to actually execute the code from another library. So, as I said, rather than rewrite it, we can just simply use Unsafe Rust to call code in other languages. And so this is unsafe because the compiler cannot guarantee that the other language is following Rust's rules for memory. So this is really, really important, right? if you were saying, like, hey, I'm going to call this C++ code or this C code, right? Rust doesn't know whether that's going to work. Rust isn't a C compiler. Rust is a Rust compiler. It doesn't know what you're going to do with memory. And so as a result, it cannot guarantee that that language is going to do the same things that Rust would. And so here's an example of that. This one line will take the pointer that my data is, and it will wipe out all of the data in it. And just overwrite it with zeros, gone. Perfectly legal in C++, right? But if you were to bring this back over to Rust now, Rust is going to be like, where'd the data go? It doesn't know, because this is not something that you would traditionally anyway do in Rust. And so Rust is not going to like this. And so this is an example of where unsafe code can become problematic, is because you're calling code that you are not able to guarantee works. And so what is really, really important here is when it comes to calling code in another language, make sure that you read the documentation for the code that's being called so that you aren't expecting anything differently than what the function is doing, because that will cause errors. So yeah, as I said, this is very, very bad, and if this were in a function you called and you weren't expecting it, it would be a problem. So another reason is high performance applications, right? And so this example, right, we have an SUV and we have a NASCAR, right? And so one of these is going to be a lot faster than the other. And that's because they removed the airbags, the headlights, who knows what else, right? There are all kinds of different changes that have been made to these cars to make them much faster. But they're not going to be as safe or easy to use for the everyday driver. And so as a result, it takes someone with a special set of skills to engage in that driving, but as a result, you're going to get more performance out of that car, right? So it really depends on keeping your skills and making sure that you're actually being more aware, as opposed to just going for a Sunday drive in your SUV where the car handles a lot of things for you. So the final reason that we're talking about today is memory mapped hardware. And so in this case, right, this is a piece of a documentation that I just found somewhere on the internet, and it shows on a certain set of chips that if your BIOS is set to a certain mode, then you can access a video output by putting in one of these addresses. And so any of these addresses will say, okay, you can set it to blink, you can set it to be red, green, or blue, you can set the foreground, you can do all kinds of different things using these memory addresses, but the way that you're able to do it is by basically just changing these values of memory. And so this is a way where you would use Rust if you didn't have any better ways to do it because the OS isn't fully running or something else. Then as a result, you're going to be using direct memory mapped hardware, or for any other reasons. There are a bunch of different reasons you would use memory mapped hardware. So let's do our first set of poll questions. So I'm going to go over here. Okay, so our first poll question is live. Why do we need unsafe Rust? Give everyone another few seconds to respond. All right, I'm going to give everyone just a little bit more time as I type in the commands to stop the poll. Okay. And I'm just entering the other command to start up the lecture. Okay, so let me just get our next one going. So the correct answer for this one is 4. There are situations where the compiler fails to verify that the correct code, or verifies correct code. And so in those situations, we need to use unsafe Rust to tell Rust exactly what we're doing. And so let me just enter the next one. Okay, So question 2, which of these is not a use case of unsafe Rust? And so while you're putting that in, I'm going to make one more quick point on memory mapped hardware because I forgot to mention this. Memory mapped hardware, one interesting thing about it is that when you're interfacing with it, the reason that we can't use safe Rust is because safe Rust doesn't know that random address that's somewhere in memory in some handbook somewhere. So the reason that we're doing that is because we want to make sure that we are actually following the documentation and everything else, because Rust can't check that for us. Rust won't go and find that documentation for us. Okay, so I'll give everyone another couple seconds here. Okay, so it looks like there were a split between 1 and 3, and so the correct answer is 1. 1. So the reason that 1 is not a use case of unsafe Rust is because we can implement parallelism in safe Rust, and that's what you'll learn on Thursday and potentially also Tuesday, depending on our schedule. But the point being is that parallelism can be done in safe Rust, whereas high-speed computing is where we're actually doing something where it may be parallel, but we're not 100% sure, right? So this could be something where we're just creating a lot of optimizations to squeeze that extra last ounce and just get that last little bit of computer power out of the machine, right? And so it doesn't necessarily mean we're using parallelism, but it could be a possibility. So let's now talk about why you should use or not use unsafe Rust. And so this, you may be unsurprised to find out, is longer than the why you should use safe Rust or unsafe Rust list. So the first reason is cheating Rust's compiler. So let's talk about this. So why shouldn't you use unsafe Rust for cheating Rust compiler? Well, it's simple. There are a very small number of issues with Rust compiler, right? And Rust compiler is almost perfect to the point where if you're running into these issues, I would be very surprised, right? It's so few and they're being fixed so quickly compared to many other languages that you likely will never see them. And even if you do, right, the likelihood of you actually seeing one of these issues is smaller than the likelihood of you thinking the compiler is doing something wrong when in fact the compiler is right. And so this is really, really important. The audio bang wasn't just you. Okay. Not sure what happened. Let me know if I need to turn down the audio a little bit. Oh, wow. Okay. Let me know if I should turn down the mic audio. So, yeah, the likelihood of you writing buggy code thinking the compiler is wrong is going to be significantly higher than the chances of you actually running into one of these issues. And it's so few that you're probably, if you're going around using unsafe Rust to get around it, you're probably doing something wrong. Most times, if you're running into an issue and you think you should use unsafe Rust, you can get away with not using unsafe Rust, and you'll usually be fine. And so don't do this, right? Don't try and think that you're smarter than Rust compiler, right? The times that you are very rare and very few and far between. And so when you see something going wrong with your code and it's not compiling, most of the time it's not going to be the compiler's fault. And when it is, you'll usually know because you'll be able to look it up and find some sort of issue that is actively being maintained. So I mentioned the first reason, but there are two of them, right? So the question is, well, what's the other reason? Well, the other one is much more important than the first one, and that's because it is undefined behavior. And so undefined behavior is really, really, really bad, in case you couldn't tell from its text being much bigger and on fire. Okay? So let's talk about undefined behavior. Okay? And I'm hearing a little bit about my production quality. Thank you. I put a small bit of effort into that. So, undefined behavior. Why shouldn't you use unsafe Rust when it comes to undefined behavior? Well, let's talk about what can happen when you have undefined behavior, right? Well, if you have undefined behavior in your code, here are some things that let's say, or here are some examples of things that could go wrong if you have undefined behavior in code that runs these things. Let's say you have an ATM, right? If you have undefined behavior in your code, someone may say that they're going to withdraw $100, and all of a sudden their account will go up to like $5 billion, right? That's just something that could happen with undefined behavior. Another example, say you write a GPS for a certain ship navigating a canal, and you have undefined behavior that slowly starts it to drift off to the side, and all of a sudden it gets stuck in a canal, causing a multi-billion-dollar shipping delay, right? That's very bad. So these undefined behaviors can add up. But you can also have, what about an airline, right? The same reason that a boat could have an issue. What if all of a sudden an airliner started saying, oh, you need to turn left, even though it was fine, just because of undefined behavior, or all the screens go dark? These are things that are not defined by nature. You could have a dam, a hydroelectric dam. All of a sudden it shuts down or it revs up, right? You can have all kinds of different issues. Even a nuclear power plant, right? And so these are all things that you have to be very, very careful of. Obviously, these industries are much more regulated when it comes to writing code. But the point is, undefined behavior is exactly that. It's undefined. You don't know for sure what will happen. And a key component to any of these systems is that when there is an issue, instead of continuing with undefined behavior that we don't know what's going on, we're going to kill the program. And so that's why if you have an out of index error, instead of just continuing running, you're just going to kill the program, right? Because you don't know what's going to happen. It could not happen in the same, it could not be the same thing if you run it 2 different times. So the key takeaway is that safe operations are always defined, no matter what the input, okay? While unsafe operations are not defined. They could vary from run to run. If I ran it the first time on my computer, but not on, and did it on the second time, if I did something wrong, it may not work the same. And this is really, really bad. And so in unsafe code, the compiler is trusting us, the programmer, to check for these invalid actions that it cannot guarantee. And if we do not try, or if we try to perform an invalid unsafe action where something isn't right, the program will do exactly what we tell it. And it will continue going on. And it will not tell anyone. And so this is really, really bad because best case scenario, you access a piece of memory that is out of bounds and you cause it to crash. However, on the other hand, it could have no effect. Or the worst case is where it silently causes a problem that doesn't affect you for years. And so somebody asks, how does it happen? How can you run the same code twice and get different results? Well, I'll show you the answer. I was right about to answer that. Why does this happen? Well, it's for a couple of reasons. And for that, we have to go back to memory management. All right? Unfortunately, we are not done treating it as a checkerboard and a series of lockers. For unsafe Rust, we have to go deeper. So we're going to talk about some pretty advanced pieces of memory here that will hopefully help you later down the line in your computer science career, but will also just be very, very important for this lecture. So the first thing is alignment. And so this is not necessarily going to help with answering our question, but it's very important for computer memory and for unsafe Rust. So when it comes to memory, right, we have these bytes. And so each byte contains 8 bits of 1 or 0, and then we have many bytes in a computer, right? And as we talked about before, it goes from 0 all the way up to hexadecimal and continues onward, right? And so here we have a couple different types. And so what you'll notice is that not all types are created equal. So a character, an ASCII character, will be 8 bits because all ASCII characters can fit within the 2 to the 8th combinations there are for characters. However, in integer, we have 32 bits, which when divided by 8, give you 4 bytes. So that's where I32 comes from, is there are 32 ones and zeros all throughout the memory telling us exactly how big this integer is. And so we say it's 4 bytes so that we have a large enough integer. If we wanted less, we could go down to like an I8 and have it be 1 byte, just like a character. So here's the important part though. When it comes to this, the way that most computers work is that they don't let you put an int in a memory address where it's not easily divisible. So for example, a character is 1 byte large, so it can go in any byte. But an integer, an I32 for the example, is 4 bytes large, so it can only go into memory addresses that are divisible by 4. 0 divided by 4, 0, good. 4 divided by 4, 1, good. 1 divided by 4, not 1, not 1, 0. It does not divide by 4, and as a result, you cannot put an integer there. And so, as you can see here, if we tried to do this, this is going to result in a problem. And so it will either, depending on the actual definition of the architecture of the computer that you're on, it will either just not work or it will be much, much slower, and you don't want that. So in general, we say that in order to avoid this, we just don't do it, right? We put things on aligned memory addresses. And so, for example, we can put 2 integers next to each other like this, and yeah, that's like the idea, right? So we always want to make sure that they are aligned to whatever is divisible by their size. So for example, we just take however many bytes it is, and then we just divide the address, and if it's divisible, then great, we are good to go. Does anyone have any questions on this before we move on to the next part of memory management for this? Yes, so somebody asked less space or different space than before. Yeah, so that's what we're getting to. So here is a very, very, very simplified example of memory. So this is, let's pretend, your memory, and so you have all the way from 0x zeros to 0xf all the way across, and this is the amount of memory you have. And so in here we just have random pieces of memory already existing, and yeah, this is just memory as it is when we start the program. And so this is where a lot of the undefined behavior that I was talking about before can come up. So let's talk about an example where we use unsafe Rust directly. So let's say we allocate and initialize some memory. So we're going to put some new memory in, and we're going to create a pointer to it so that we can access it later. So now we can go access that data, we can do whatever, and when we're done, what we're going to do is we're going to deallocate that memory. So when we do that, what's going to happen is this memory, this orange block right here, is going to go away. But the pointer will still exist, and we can still use this pointer to access the memory that is in this spot. Now at this point, right, if we tried to access this pointer, it would crash because this memory is no longer assigned to our program. However, let's say we keep this pointer around and on some other thread, we add some new memory, right? So now we add this purple memory. And so this might be on a different alignment. It could be many other things. And so all kinds of different things can be happening, and we don't know, right? This all depends on the runtime of the program. And as a result, we don't know exactly what's going to be there. It could be this purple memory. It could not be. We just don't know. And the issue is that when this pointer is now pointing to memory that we don't know what's going on, what happens if we try to access or modify that old pointer, right? It could be fine. We could simply just read this pointer and just get some garbage data, and it could cause an issue. But it could also overwrite this data and make this entire data corrupted, right? We don't know what is going on. We might say, oh, this is a integer, when in reality it's a float, right? We don't know how things are going to change, and that's really, really bad, especially if we try and access something that might not be as aligned in the same way that our data was. We could have bad things. And for this, let's talk a little bit about invalid binary values. So don't worry, this is the final part of memory that we're going to talk about in depth like this. So invalid binary values are values that aren't defined. I know, crazy idea. We're talking a lot about definitions. So take, for example, these 2 pieces of memory that I have right here, right? So one of them says 0100, 0110, and the other one is just all ones. So as I had mentioned before, we're using ASCII, which is the American Standard Code for Information Interchange, And so when we decode these 8 bits into a character, what we're going to get is the letter F, right? And so we now know, okay, cool. ASCII says this is an F. Cool. We now have an F in our character. But what if we try and decode this all set of ones? Well, it's not defined. Nobody said, here's what all the ones are, right? ASCII doesn't go up to all ones because they didn't need it. So what do? Right? Well, let's take a look at this table, right? And so if we look here, we can go and look and turn these binary values into hexadecimal. So that's what I did right here. As before, we have 46. So if we go to 46 in hexadecimal, you'll see that's F. But if we try and go to all ones, which is FF, you'll notice we stop at 7F. So we don't actually have a character that is FF, because 7F only goes up to all ones except for this last one. So as a result, it's just not defined. And so what will happen depending on your computer is you'll usually get like a question mark or like an empty box or some sort of other symbol when it can't decode what character it's supposed to be. And so that's what's going on here is if we try and access data, if this was a character and this purple data is an int, and this int has all ones here, and we try and dereference the pointer that is ones just because it's an integer now, it could just not work. And so this is where it becomes very, very important to be aware that if you're trying to dereference a dangling pointer, which is what it's called when you leave a pointer that is not in the same that's pointing to a piece of memory that is now no longer valid. There we go. Then you're going to run into issues, and you could run into invalid binary values, which is bad. So, in summary, right? How do we prevent undefined behavior? Well, Unsafe Rust is all about telling the compiler that we did our due diligence, and we guarantee that the unsafe code always follows the rule of Rust. At all times when we are writing unsafe code, we always are following Rust's rules, right? We need to tell it, we did your job better than you did, Rust compiler. We know what we're doing. And so what are the rules, right? Well, unsafe Rust code must never, ever, 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 ever dereference a dangling, deallocated, a dangling, which means deallocated, or misaligned pointer, right? This is what we just talked about. It must never have a data race to write to the same piece of memory. More on this during the concurrency lectures with Eustace. Data races are really, really bad when you're working with unsafe Rust and raw memory because you could run into issues where you might modify the same piece of memory. So data races are very bad when you're using unsafe Rust. It could create invalid binary values. You don't want that when you're writing unsafe Rust. You must never do that. And then it has a bunch of other rules that I'll talk about how to find them later, but it can never do any of them. So let's go to our next set of poll questions. So this is going to be asking whether a variable is correctly aligned, or whether a piece of data is correctly aligned. I know, unsafe Rust having rules. It's almost like we have rules around doing dangerous things so that we don't do them badly. All right, so I'm going to close up the poll. Okay, so it looks like most of you were right and put 1, which is true. And that's because, as I mentioned, a character is only 1 byte, and I put it right here just in case you forgot. And because it's only 1 byte, it's divisible by any of these, right? 4 divided by 1 is correct, or 4 is divisible by 1. So let's go to the next question. So, is this variable correctly aligned? All right, I'm going to close the poll. Okay, so everyone got this correct. It's false, and that's because 4 bytes are not divisible by 2, so everyone's correct. It is not correctly aligned. What about now? Let me create the next poll. So take your time. All right, it looks like everyone's done, so I'm going to close it. Okay, so everyone put 1, which is correct. Remember, 4 bytes. 4 is divisible by 4. We are good to go. How about now? Pulled a bit of a switcheroo on you. I'll see. In case any of you are wondering, A is 10, B is 11, C is 12. Okay, I have closed the poll. Correct answer is true. I pulled this mostly as a switcheroo and just to check that everyone knows hexadecimal. C is 12. 12 divided by 4 is 0 or is 1, so 12 is divisible by 4 or is 3. Wow. I don't know how I messed up dividing there, but anyway, 12 divided by 4 is 3, so it is divisible, and that means that we are good to go. So, should you write unsafe Rust? Well, the answer is complicated, but in general, yes. Unsafe Rust is a great tool, and it will solve a bunch of issues, right? It helps you solve issues that the compiler cannot check. However, when you're writing unsafe Rust, you need to be sure that you need to use it, right? When you're writing unsafe Rust, you need to be very careful to not write too much of it, because unsafe Rust is a great way to cause bugs. Whereas if you're writing safe Rust, then you're less likely to make those bugs. So how do we write good unsafe Rust? Well, there are a bunch of answers, but here are some of them. The first one is making sure you actually need to write unsafe code, right? As I just mentioned, if you don't need to, don't write unsafe code. You'll save yourself a lot of trouble. But make sure that you actually really need to write unsafe code, right? Don't just say, oh yeah, I need to write unsafe code. Double check. And you know what? While we're at it, don't write unsafe code unless you're absolutely sure you need to, right? So now that we're good and checked and we've made sure that we need to write unsafe Rust, read the Nomicon. So the Nomicon is this amazing thing. Let me see if I can find it. Okay, it's disappeared on me. Anyway, the Nomicon, I know, mixed messages, but the Nomicon is a fun book about the dark arts of unsafe Rust. And you can read this warning for yourself. The knowledge is provided as is without warranties, so on and so forth. Don't shatter your psyche and set your mind adrift into the unknowably infinite cosmos. Fun, right? So, the Rust Nomicon is great because it will tell you everything to avoid when writing unsafe Rust, but it's also a very long book that you need to know in order to write unsafe Rust, or at least in order to write it with 100% certainty. So if you're going to write unsafe Rust, make sure that you know at least generally everything inside of this. You don't need to know it cover to cover, but just know everything that it talks about at the very least. And if you think that you're doing something that it would not want, go check and read it again. So, be careful when writing unsafe Rust, because after you read the Nomicon, your mind and psyche may be shattered. But if you're pair programming, someone else might be able to help catch an error, right? if you've read the Nomicon, you can now go and check and read Unsafe Rust and have someone else with you and hopefully catching bugs while you're trying to write some of the more boilerplate code and not paying as much attention potentially. So be very, very careful while you're writing it and try to have a second set of eyes on it, if not more. And then finally, or second to last, properly document all of your calls to Unsafe Rust. If you write safe code that does something your Unsafe Rust code doesn't expect, even though the Unsafe Rust code looked good when you wrote it, it's now no longer going to work correctly. And so whenever you're using Unsafe Rust, be sure to tell the person who's going to use it as safe code that you're actually doing that in case it causes an issue later on. So you need to be very careful to tell everyone that when you're using Unsafe Rust that you need to be aware that someone's written Unsafe Rust that you're now calling. And then finally, run Miri. And so Miri is a great tool that we're going to have a quick aside on. So Miri is an interpreter for Rust, which is great. So what it will do is it will, similarly to the Python interpreter, run alongside your Rust code, and it will run it as if it's line by line. And it will keep track of a bunch of different things. And it will warn you when you do any of these things. It will tell you if you have an out-of-bounds memory access, so a dangling pointer. It will tell you if you're trying to access memory that isn't aligned properly. It will tell you if you leak memory, meaning that all of the pointers are gone, but you haven't deallocated that memory. It will also tell you a bunch of other things that I'm not going to get into. Miri is a great tool, so use it when you can, because Miri will save you, and whenever you're writing Unsafe Rust, you should run Miri after you've run the initial test. So, all that out of the way. We've talked about all the issues, we've talked about how to write it, or we've talked about why you should or shouldn't. Let's actually talk about writing Unsafe Rust, right? I know, super exciting. We've got 3 lines and none of them say unsafe. But this is how we get started with our Unsafe Rust journey. So what we're doing here is we're saying let this number equal 5, and then let R1, which is a immutable raw pointer, okay? So what this means is we're saying, okay, here's num, and we use the same symbol as borrowing, this and, to say we want a reference to num, and we want it as a pointer to a constant integer. So what we're saying here is give us the memory address of num and give it to us as a pointer to an integer, because 5 is an integer, right? And the reason we have const there is that it tells us, okay, we have a pointer to this memory, but we cannot modify it, right? We don't want to change any of this memory. However, we can also create a mutable pointer. And so this is the same thing, except we say, give me num, or a reference to num as a mutable pointer, or give me a mutable reference to num. And so this is, remember, just the same idea as borrowing, right? We have and mute, and then the name, as, and so we're casting it as a mutable pointer to an integer. And so this is the same line as above, but it allows us to modify the memory underneath. And so we can do that by taking a look at this next line. And so what this does is it allows us to say, okay, now that we have these memory addresses, let's print out what the value is. And so if we run this code, you'll see that it says R1 is 5, R2 is 5. We're good, right? We have now accessed memory unsafely. However, what if we do this? We're going to say, okay, and by the way, I should probably mention this going back to the slide. The reason we have the star here is because now that this is a pointer, if we just returned R1 and R2, which you'll see in a minute, it will give us the actual memory address. So it'll say 0x and then whatever the memory address is. What we want is the data inside. So what this star does is it tells us to dereference that data. And it says, okay, go to this memory address that you have in this variable and then give me that instead of just the variable itself. And so, as I said, it gives us 5 in both cases. We're good. But what if we say, okay, give us the address, or give us the value of R2, right? The value of the memory in R2, and then add 1 to it, and then set the value of the memory in R2 equal to this value. What is going to happen, right? What are we going to print? Well, here's an interesting thing. R1 becomes 6. Crazy, right? This is an example of an error that you can have by writing unsafe code. So despite not changing R1, R1 has changed, even though it's even marked as a constant variable, right? We said, hey, this is a constant value, but we were able to change the memory by going around this value. We said, okay, not our problem. We're just going to create another memory address or get another pointer to it, and we're going to say, okay, let's modify the memory that way. And both cases of this memory change, and the best way to see that is if we go ahead and we show this example, right? So what we're doing is we're saying, okay, here's R1. R1 points to some data somewhere. And now we're going to create R2, which is mutable, and we're going to point it to the same data. And so rather than changing some value in R2, what we're doing is we're changing this data that both of these point to. And so there you go. You can now see it's different data. I know, crazy, right? Animations. But anyway, we have R1 and R2. And so now that we've changed the data through R2, when we access these, both of them will now be updated, right? We're changing the underlying data and going around R1 instead of through R1, which is very, very bad. So let's take a look at that by looking at this code. So what we're doing here is instead of printing out the values of the pointers, we're printing out the pointers themselves. And if you look, you're going to see that they're the same, right? You can take a look. You can read 7FF DB987A044. Both of them are the exact same pointer, which I know, crazy idea, right? They're pointing to the exact same data. So even though we might try to change one, when we change one, we're changing the other. So let's talk about calling external code now that we've talked a little bit about memory. So here's an example of us trying to call some C code. And so this first part here is we're saying, okay, there's an external function that the Rust linker has connected to our code. And it's written in C, and it's a function called absolute value, or ABS, and it will take an input of an I32, an integer, and return an I32, an integer. And so what you have to keep in mind is that there is an ABS function built into C. And this ABS function will take an int in C, but you notice we don't say int, we say I32. And that's because, remember, C is not Rust. Rust is not C. So we have to be able to convert between the two and double check and make sure everything's right. So this is an example of where you wouldn't want to use usize because you don't know if you're using a 64-bit machine and this function is only going to take in an I32. But what it allows us to do is say in our main function, I have some unsafe code where I'm going to print the absolute value of -3 according to C is -3, or is 3, right? And so if we do that, you see we get 3. And what's important here is keeping in mind, we gave -3, right? If I made this a variable up here, like if I said let my value equal 3 and then put my value here, that would still work. But this C function could wipe out the memory in my value. Gone. Poof. And if that happens, if I try to call my value down here, it wouldn't work, which is obviously really bad. And that's that example of why this is unsafe. So now let's talk about other code calling Rust, which isn't unsafe Rust, but we're going to talk about it because while we're here, right? So this is a function that is going to call be called by C. So what we say is we say nomangle, which basically tells the Rust compiler, hey, don't change the name of this function because someone else is going to use it, right? Because every compiler changes the name of functions differently based on how the compiler is written. Nomangle will say, okay, don't do that for this because C needs to use it. And then we say, okay, we have a function that's written for an external language C, and we're going to say, okay, in this function, just print a line. And so this would work. I don't have an example of it because it's pretty simple, but this is how you would do it. You could obviously change the inputs and outputs, and then you just need to link it to your C code. Okay. I know that was a little bit fast, but we are going to do one more round of poll questions. So let me set up bot. Okay. What is the output of this program? Okay, I'm going to close the poll. All right, so the correct answer, surprisingly to apparently all of you, is 2. Nobody got this one right. So let's talk about this because apparently this is something that's a little bit confusing. So what we're doing here is we're saying, okay, we have this number 5, and that's num, okay? And so now we're taking num, we're saying, okay, get me the reference to num, and make it a const I32. So we're saying, okay, give me a pointer to num. So now R1 is going to be equal to, say, 0x7FFEEFBFF4CC. And so now that we have that, here's where I tripped you up. I said let R2 equal to a reference to R1. So now R2 is referencing R1, and so what we do in this unsafe code is we say, okay, so we now have the pointer to R1, but I want the pointer, I want the data in that pointer, right? So what we do is we take R2, and R2 is pointing to R1, so we go, okay, what's in R1? Well, it's a pointer to num, right? Because we are just dereferencing it and looking at that value. So now the second question. I love the bandwagon effect of everyone seeing that someone put down a certain answer in Pollbot and then selecting the same answer. And the fact that I marked this as Q7 even though it's Q8. Anyway, let me check that everyone did. It is hard. I'm not disagreeing with you. Okay, so now that I've closed the poll, one person got it right. One person did not follow the bandwagon and put 2. And so the reason that this is happening is instead of the craziness that I did last time, I've changed that up. So what I did last time is I just took the memory address of R1. So instead, what I'm doing this time is I'm cloning R1. So I'm saying, okay, give me that address, and then give me the address of that. So this line essentially does nothing new. This line is just to throw you off. The key to this question that you should have seen is the fact that we have 2 stars instead of 1 now. And because we have 2 stars, we're able to say, okay, we have R2, let's dereference it. And so what R2 gives us is like 07xFFEEB or FBFF4CC. And then we say, okay, take that, dereference it again. And so this is basically the game of ask person A, and person A tells you to ask person B, and person B tells you the answer, right? And so 0x7f blah, blah, blah gives us the value of num, which is 5. And so that's why we get 1 this time. So I know this is very hard, and I know this is like fairly difficult, especially for freshmen, just kind of dipping your toes into Rust. But the point of this lecture is to, or these poll questions specifically, is to show you why you probably shouldn't write unsafe Rust right now, right? I'm not saying you shouldn't forever. I'm saying you should. But I'm saying that you should only once you actually understand it, which I could never have taught you in a 50-minute lecture. So, I know that was a lot, but we have 2 slides that I'm going to talk about. Well, 1 slide, and then I've got an end card slide. So, announcements. I know we don't usually do this, but I figured it was appropriate given that it's the end of the semester and we have a couple things to mention. First, as you may have seen in the announcements channel, Rust 3 deadline got extended to 11:59 p.m. Central Daylight Time on May 5th. So this means you have from now until the end of the semester to finish Rust 3, whatever that means for you. We decided to do this mostly just to de-stress everyone and hopefully give a little bit of a break as we head into the most stressful part of the semester, and we know that a lot of other classes are probably causing a lot of stress for people, so we decided that instead of pushing a bunch of other homeworks, because we had a few left, we just wanted to end it at Rust 3. So Rust 3 is your last homework, and while you can take until May 5th, you should also keep in mind that if you want, you can finish it earlier, and that way you can focus on your other classes. So the next thing is extra credit feedback form is coming soon. This is really, really important. This helps us know what to do next semester and how to make changes that help us figure out what went wrong and what went right. So for example, you could all put debugging homework was terrible, and we would then be able to say, okay, well, everyone hated debugging homework. Let's fix it for next semester. So this is really, really important for the extra credit feedback form, and we'll talk more about that once we have everything finalized, but it will be a significant amount of extra credit. And then some other changes may be coming as we continue going through the last couple weeks here. We're talking about potentially some changes to the lecture schedule and anything else, but for the most part, this is meant to de-stress you. We are not going to try and give anything more difficult. Now, one final thing. This is my final lecture as of right now. Unless the schedule changes, this was my final lecture of the semester. So I did want to take a moment and say thank you all for being great at sticking with this and for coming on this crazy journey with us for CS196. I hope you learned a lot. I hope your lectures with Eustace for the rest of the semester are going to go well. And yeah, thanks. All right, I'm going to call it there.